Marc Belanger Test on Gerard Morin Post-Transformers Over-Unity AC Circuit Analysis, presented by Tim Lee, April 2018. My name is Tim Lee. I am 66 years old, living in Singapore. I am a retired engineer, experienced in electromechanical repair and maintenance of steam sterilization equipment in hospitals. I wish to share with the knowledge seekers that I did an AC circuit analysis to add on to the knowledge to extend my understanding of Marc Belanger's test on Gerard Morin pole transformers over unity circuit. Test on Gerard Morin pole transformers over unity circuit consists of two pole transformers in cascade connection, one 15 kVA, the other 10 kVA capacity, both rated at 13,800 volts. It was experimentally demonstrated that with wattmeter output 921 watt, a petrol-run electric generator supplied 120 volt, 60 Hz, 8 ampere. There was a 91 watt loss at low 830 watt soldering iron. The over-unity test failed. Source: Gerard Morin generator transformer experiments. Concepts: the AC circuit analysis is done by applying concepts of ideal transformers, voltage source, current sources in modeling the circuit. Ideal transformers, their VA capacities are conserved in the cores without power loss, so that the VA in the primary winding equal VA in the secondary winding. Vin, A-in equal to Vout times A-out. Voltage sources. Their internal resistance are infinitively high, so that they do not take any current across to measure the voltages. I equal to V over Rin equal to 0, or Rin equal to infinity. Current sources. Their internal resistances are 0, so that they do not take any voltage across to measure the current. V equal to I times Rin equal to 0. Rin equal to 0. The 921 watt electric generator. This means the wattmeter is measuring power output from the generator. 921 watt equal to 0.921 kilowatt. The generator is delivering electrical energy equal to 921 watt equal to 921 VA. When this electrical energy is input into the 15 kVA pole transformer at 120 volt, its available current is 921 VA divided by 120 volt equal to 7.675 ampere. Note: electrical power equal to V times I cosine theta equal to VA when resistive load cosine 0 equal to 1. Theta is the phase angle between the volt V and current I. Volt is Newton meter per coulomb. Ampere is coulomb per second. The coulomb terms got cancelled out in the multiplication. Generally speaking, VA is the energy capacity. Kilowatt is the energy consumption. VA and watt are of the same dimensional units, volt amperes, Newton meter per second, kilogram meter square per second cube, mL square T to the power minus 3. The load, 1 soldering iron equal to 930 watt. Power RL equal to 830 watt at 120 volt. RL equal to 120 square divided by 830 equal to 17.349 ohm. Current IRL equal to 120 volt divided by 17.349 ohm equal to 6.9168 ampere. Note: power P equal to I square R equal to V divided by R square times R equal to V square divided by R. R equal to V square divided by P. The input transformer capacity is 15 kVA. This means it can take up to 15 kVA from the electric pole. It can supply up to 15,000 VA divided by 120 volt equal to 125 ampere at 120 volt output. Likewise, 15,000 VA divided by 13,800 volt equal to 1.0870 ampere at 13,800 volt input. X2 equal to 120 divided by 15,000 divided by 120 equal to 0.96 ohm on the low voltage side. X1 equal to 13,800 divided by 15,000 divided by 13,800 equal to 12,696 ohm on the high voltage side. In this circuit, the 15 kVA transformer is run reversed. The input is connected to the low voltage side at 120 volt AC from the generator. So the high voltage side is by induction from the input 120 volt AC. The output voltage would depend on its turn ratio, N equal to 115 as given by the step-up transformer formula. V out equal to N times V in. Step down, V in divided by V out equal to N. 13,800 divided by 120 equal to 115 equal to N. Therefore, its maximum induced high voltage V1 equal to 115 times 120 equal to 13,800 volt AC or 13.8 kV as rated. The output transformer capacity is 10 kVA. This means it can take up to 10 kVA from the electric pole. It can supply up to 10,000 VA divided by 120 volt equal to 83.3333 ampere at 120 volt output. Likewise, 10,000 VA divided by 13,800 volt equal to 0.7246 ampere at 13,800 volt input. X4 equal to 120 divided by 10,000 divided by 120 equal to 1.44 ohm on the low voltage side. X3 equal to 13,800 divided by 10,000 divided by 13,800 equal to 19,044 ohm on the high voltage side. In this circuit, the 10 kVA transformer is run forward as a normal steps down. The input is connected to the high voltage side at induced V1 equal to V3 equal to 13,800 volt AC. This high voltage is stepped down by the transformer into low voltage. V in divided by N equal to 13,800 divided by 115 equal to 120 volt equal to V out. The Gerard Morin pole transformers over unity circuit. It consists of two pole transformers in cascade connection. The input Vi is connected to 120 volt AC generator. Vi equal to 120 volt. The output Vo is connected to 120 volt AC load. Vo equal to 120 volt. In between, the high voltage coils are connected in parallel with the red lines in the circuit. I shall now replace the primary and the secondary coils with their resistance, calculated as above, into the ideal transformer model. 15 kVA, X2 equal to 120 divided by 15,000 divided by 120 equal to 0.96 ohm on the low voltage side. X1 equal to 13,800 divided by 15,000 divided by 13,800 equal to 12,696 ohm on the high voltage side. 10 kVA, X4 equal to 120 divided by 10,000 divided by 120 equal to 1.44 ohm on the low voltage side. X3 equal to 13,800 divided by 10,000 divided by 13,800 equal to 19,044 ohm, high voltage side. The input circuit. From the electric generator, 921 watt equal to 921 VA. I in equal to 921 VA divided by 120 volt equal to 7.675 ampere. The 15 kVA pole transformer has very low resistance, X2 equal to 0.96 ohm. It can take up to 125 ampere as rated. Hence, it is not a problem to take 7.675 ampere. The input current from the generator is measured by the wattmeter. The wattmeter measures wattage, 921 watt. We can relate it back to current flow as 0.675 ampere. The mechanical energy convertible into electrical is 921 VA, calculated above. These 7.675 ampere shall consume energy in X2 as 7.675 square times 0.96 equal to 56.5494 VA. The Cascade circuit. The secondary second transformer is connected by the red line. V1 and V3 are the same. V1 equal to V3 equal to 13,800 volt AC. When 7.675 ampere current, as in wattmeter, is fed into the 15 kVA transformer, its input energy equal to 7.675 times 120 equal to 921 VA. X1 and X3 are connected in parallel. The combined resistance is X1 parallel X3 equal to X1 times X3 divided by X1 plus X3 equal to 12,696 times 19,044 divided by 12,696 plus 19,044 equal to 12,696 times 19,044 divided by 31,740 equal to 7,617.6 ohm. Total current I1 transferable from the generator to X1 parallel X3 equal to 9,000 to 9,021 VA divided by 13,800 volt equal to 0.06674 ampere. The power consumption in the Cascade circuit equal to total current square times X1 parallel X3 equal to 0.06674 square times 7,617.6 equal to 33.9305 watt equal to 33.9305 VA. The output circuit. The secondary transformer 10 kVA is normal step down. Open circuit response. When the load is not connected, off. The VA consumption accounted for in X2 to X1 parallel X3 to the 10 kVA output transformer equal to X2 consumption plus X1 parallel X3 consumption equal to 56.5494 plus 33.9305 equal to 90.4799 VA. The output current in the 10 kVA transformer IX4 equal to 90.4799 VA divided by 120 volt equal to 0.7540 ampere at low load. Open circuit current. This is the leakage current at X4 required to maintain 120 volt output. This IX4 equal to 0.7540 ampere shall have output power consumption in X4 equal to 0.7540 square times 1.44 equal to 0.8187 VA. This 0.8187 VA shall be accounted for in the total current I1 in X1, X3. Load response. When the 830 watt soldering iron is connected on, the load RL 120 square divided by 830 equal to 17.3494 ohm. Current IRL equal to 830 VA divided by 120 volt equal to 6.9167 ampere. Total current required IO equal to IRL plus IX4 equal to 6.9167 plus 0.7540 equal to 7.6707 ampere. VA required in X4 to support the load equal to 120 times 7.6707 equal to 920.484 VA, almost the same reading as the wattmeter. Total current I1 required in X1 parallel X3 to support the load equal to 920.484 VA divided by 13,800 volt equal to 0.0667 ampere. This total current I1 is now become a demand in the Cascade circuit X1 parallel X3 equal to 7,617.6 ohm. The power consumption in the Cascade circuit equal to total current square times X1 parallel X3 equal to 0.0667 square times 7,617.6 equal to 33.8899 VA. The power consumption in the X1 parallel X3 Cascade circuit, it shall effect a demand in the input X2. 33.8899 VA divided by 120 volt equal to 0.2824 ampere. This total current I1 equal to 0.0667 ampere in the X1 parallel X3 circuit. It shall demand current in X2 as I in equal to 0.0667 times 13,800 divided by 120 equal to 7.6705 ampere. This 7.6705 ampere created consumption in the 15 kVA transformer X2 equal to 7.6705 square times 0.96 equal to 56.4831 VA. Total energy required from the generator to support the 830 watt load equal to X1 parallel X3 consumption plus X2 consumption equal to 34.4613 plus 56.4831 equal to 90.9444 VA. This 90.9444 VA is equivalent to total demand in X2. 90.9444 VA divided by 120 volt equal to 0.7579 ampere. Current amplification equal to output demand divided by input demand equal to 6.9167 divided by 0.7579 equal to 9.1261 over unity. VA equal to 90.9444 VA equal to 90.9444 VA divided by 740 equal to 0.1218 horsepower. This indicated that 0.1219 horsepower, 90.9444 watt is sufficient to support the load at 830 watt. In conventional measurement by the wattmeter, it indicates the current and voltage flow as watts. 830 divided by 921 equal to 0.901 below unity. 921 minus 830 watt equal to 91 watt was lost, therefore failed the over-unity test. Continue simulation. 5.5 loading response. In this AC circuit analysis, it accounted for theoretical energy consumption versus the current flow. Since the above calculation indicated only 90.9444 watt was consumed, there is energy available to support a larger load. I continue to calculate with larger simulated load. This factor of 5.5 times loading is obtained by repeat calculation with 2.5, 3.5, 4.5, etc. until the consumption matches the input. When the loading is 5.5 times, 830 times 5.5 equal to 4,565 watt. Current demand from load RL equal to 4,565 divided by 120 equal to 38.0417 ampere. And the generator is unchanged at 921 watt or 1.2346 horsepower, 8 ampere. Open circuit. When the load is not connected, off. The output current that is transferable in X3 from the 921 watt generator output equal to 7.675 ampere as calculated above. The output current in the 10 kVA transformer IX4 equal to 0.7540 ampere. At low load, open circuit current is unchanged. This is also the current at X4 required to maintain 120 volt output. Total current required I0 equal to IRL plus IX4 equal to 38.4017 plus 0.7540 equal to 39.1557 ampere. VA required in X4 to support a 5.5 loading equal to 39.1557 times 120 equal to 4,698.4684 VA. The current required in X1 parallel X3 to support the 5.5 loading equal to 4,698.684 divided by 13,800 equal to 0.3405 ampere. This I1 equal to 0.3405 ampere is total current required to support the 5.5 loading at 4.565 kilowatt with 921 watt generator output. This total current I1 equal to 0.3405 ampere. Demand in the Cascade circuit X1 parallel X3 shall consume 0.3405 square times 7,617.6 equal to 883.1864 VA. This 883.1864 VA shall demand in the 15 kVA transformer back to the input at X2. 883.1864 VA divided by 120 volt equal to 7.3599 ampere. This 7.3599 ampere shall consume in X2 7.3599 square times 0.96 equal to 52.0014 VA. Total consumption in X2 equal to 883.1864 plus 52.0014 equal to 935.1878 VA. This 935.1878 VA divided by 120 volt equal to 7.7923 ampere, equivalent to 935.1878 divided by 746 equal to 1.2536 horsepower. This calculation indicated that the 921 watt 1.2346 horsepower generator is sufficient to support 4.565 kilowatt loading. It shall require 7.7923 ampere and an 8 ampere fuse shall not be blown. 135.1878 VA divided by 120 volt equal to 7.7932 ampere is within the capacity of the 15 kVA pole transformer. Current amplification equal to 38.0417 divided by 7.7932 equal to 4.8814 over unity at 4.565 kilowatt loading. Note: 5.5 times loading at 4.565 kilowatt generator required shall be 1.2536 horsepower. It cannot go higher loading already, as the 8 ampere fuse shall be at the verge of being blown. In conventional measurement, the watt meter is measuring the current flow. As long as that current 7.675 ampere is flowing across the meter, it shall indicate 921 watt. This generator is running. It keeps the current flowing. If no consumption, the generator's engine shall run easy. So it could be current amplification equal to 38.0417 divided by 7.675 equal to 4.9566 at 5.5 loading, 4.565 kilowatt. The previous loading, 830 watt, would be 6.9167 divided by 7.675 equal to 0.9012. This indicated how the over-unity test failed. Short circuit response, full load. When the 830 watt load is short-circuited, it shall demand full load current at the output X4. On the 10 kVA transformer, its full load current IRL is equal to 10,000 VA divided by 120 volt equal to 83.33333 ampere on the low voltage side. Its full load current I3 equal to 10,000 VA divided by 13,800 volt equal to 0.7246 ampere on the high voltage side. This total current I0 equal to IRL plus IX4 equal to 83.3333 plus 0.7537 equal to 84.087 shall demand on the cascade circuit X1 parallel X3. I1 equal to 84.087 times 120 divided by 13,800 equal to 0.7312 ampere. X1 parallel X3 consumption equal to 0.7312 square times 7,617.6 equal to 4,072.7760 VA divided by 120 volt equal to 33.9398 ampere at the input X2. This 33.9398 ampere demand, when reflected back to input from generator, it shall consume energy at X2. 33.9398 square times 0.96 equal to 1,105.8336 VA. Total VA required from the generator equal to 4,072.7760 plus 1,105.8336 equal to 5,178.6096 VA. This 5,178.6096 VA divided by 120 volt equal to 43.1551 ampere. Current amplification equal to 83.3333 divided by 43.1551 equal to 1.9310 over unity at full load. This shall require a generator of 5,178.6096 VA equal to 5.179 kilowatt equal to 6.9418 horsepower. A 7 horsepower equal to 5.2 kilowatt generator shall affect the output circuit current I4 at X4 and VA consumption in X2. I shall need to calculate again to make sure that the demand is within 7 horsepower. After simulation, as in the next slide, it indicated 8.759 horsepower. or a round off to 9 horsepower is required. Calculate 7 horsepower again. The total current I1 transferable from a 7 horsepower generator equal to 7 times 746 divided by 13,800 equal to 0.3784 ampere. The current 0.3784 ampere shall consume in X1 parallel X3 equal to 0.3784 square times 7,617.6 equal to 1091 VA. Open circuit. When the load is not connected, is off. The VA that is transferable in X1 to parallel X3 to the 10 kVA transformer to X4 equal to 1091 VA. The output current in the 10 kVA transformer I0 equal to IX4 equal to 1091 VA divided by 120 volt equal to 9.0898 ampere at low load open circuit. This is also the current at X4 required to maintain 120 volt output. When the load RL is short circuit, full load current 83.3333 ampere is on. Total current demand on the full load I0 equal to IRL plus IX4 equal to 83.3333 plus 9.0898 equal to 92.4231 ampere. VA required in X4 to support 92.4231 ampere equal to 92.4231 times 120 equal to 11,090.772 VA. The current I1 required in X1 parallel X3 to support 92.4231 ampere equal to 11,090.772 divided by 13,800 equal to 0.8037 ampere. This 0.8037 ampere created consumption in X1 parallel X3 equal to 0.8037 square times 7,617.6 equal to 4,920.4645 VA. This 4,920.4645 VA created demand at X2 equal to 4,920.4645 divided by 120 equal to 41 ampere. This 41 ampere demand also consumed energy in X2 equal to 41 square times 0.96 equal to 1,613.76 VA. Total energy required from the generator equal to 4,920.4645 plus 1,613.76 equal to 6,034.2245 VA. 6,534.2245 VA is also 6,534.2245 watt equal to 8.7590 horsepower. This indicated that generator to be settled down between 7 horsepower to 9 horsepower is sufficient to cover the full load. Short circuit loading 83.3333 ampere. When the generator is upgraded to 9 horsepower, the leakage current IX4 will be greater than 9.0898 ampere. The 9 kVA would be overload at 92.4231 ampere. It may even burn out the 10 kVA pole transformer. The generator upgrade should stop at 7 horsepower. 7 times 746 divided by 120 equal to 43.5167 ampere. Current amplification 83.3333 divided by 43.5167 equal to 1.9150 over unity at short circuit overload. To avoid power trip, 80 ampere circuit breaker CB2 to be installed. Summary: the Marc Belanger test pole transformer combination was 15 kVA to 10 kVA. Current amplification 9.1261. Generator 1.2346 horsepower. Generator 0.921 kilowatt. Load 0.83 kilowatt. Maximum load 4.565 kilowatt. Current amplification 4.8814. Full load output 83.3333 ampere. Current amplification 1.915. Generator required 7 horsepower. Circuit breaker CB1 43 ampere. Circuit breaker CB2 80 ampere. The pole transformer characteristics: 15 kVA, X1 12,696 ohm, X2 0.96 ohm, 10 kVA, X3 19,044 ohm, X4 1.44 ohm, X1 parallel X3 7,617.6 ohm. Appendix: current amplification. As shown in this AC circuit analysis, it indicated that the Gerard Morin Over-Unity was achieved in the Cascade circuit by X1 parallel X3, which lowered the resistance to 7,617.6 ohm. Also, the voltage being stepped up to 13,800 volt reduced the total current in X1 parallel X3. The VA consumption, total current square times X1 parallel X3, is reduced. It gives more current available from the generator to support a larger load. As calculated in previous slides, the VA required in the input to Cascade to output are respectively 91.8969 VA to 34.4613 VA to 928.248 VA with 921 watt generator, 830 watt load. Conservation of energy. In a step-up transformer, as in the 15 kVA pole transformer, being run in reverse. There is current amplification because of its turn ratio N. In a step-up transformer, the energy capacity VA has conservation. V in times A in equal to V out times A out equal to N times V in times A out equal to 115 times V in times A out. Imply that A in equal to 115 times A out. V in as a common factor got cancelled out, resulting A in can amplify A out by N equal to 115 times. Though A out is always smaller than A in, conversely, A out equal to 1 over N times A in. Appendix VA in output. In the output, I took V voltage times ampere equal to VA required. A 830 watt load at 120 volt required IR equal to 830 divided by 120 equal to 6.9167 ampere. In open circuit, the leakage current is to maintain 120 volt. I0 equal to Ix4 equal to 0.754 ampere. Total current to support the load I0 equal to IRL plus Ix4 equal to 6.9167 plus 0.754 equal to 7.6707 ampere. VA required equal to 120 times 7.6707 equal to 920.484 VA. RL equal to 120 square divided by 830 equal to 17.3494 ohm. X4 equal to 1.44 ohm. VA required equal to 6.9167 square times 17.3494 plus 0.754 times 120 equal to 830.0081 plus 90.48 equal to 920.4881 VA. These indicated that 2.466 ampere is used to maintain 120 volt. Its consumption 0.754 square times 1.44 equal to 0.8187 VA. Their total consumption equal to 830.0081 plus 0.8187 equal to 830.8368 VA would be a smaller value. Conclusion. In this AC circuit analysis, it is indicated that there is current amplification 9.1261 over unity at 830 watt load due to reduced VA consumption. In one-pole transformer 15 kVA, there is step-up voltage amplification from 120 volt to high voltage 13,800 volt. The other pole transformer 10 kVA, there is step-down voltage suppression 13,800 volt to 120 volt. By cascading two pieces pole transformers, 15 kVA to 10 kVA capacity. The total VA consumption in the input circuit X2, X1 parallel X3, the VA equal to 90.3744 VA equal to 90.3744 VA divided by 746 equal to 0.1211 horsepower within the generator's 921 watt-meter reading. At 5.5 loading, 4.565 kilowatt, the current amplification falls to 4.8814. The 921 watt generator output is sufficient to support the low 4,565 watt load. The short circuit response indicated at 10 kVA full load, 83.3333 ampere. The current amplification is 1.9150, and the generator needs to increase to 7 horsepower to support the full load output to low at 83.3333 ampere, equal to 83.3333 times 120 equal to 10,000 VA as the 10 kVA pole transformer rated. Conclusion: the low voltage input on the 15 kVA, it has low resistance, X2 equal to 0.96 ohm. It can easily take in high current. It shall have current surge. It can lead to power trip. It is not suitable to plug in to the wall socket. 43 ampere circuit breaker CB1 to be installed for the 921 watt 1.2346 horsepower generator protection to limit the short circuit loading at 83.3333 ampere. 80 ampere circuit breaker CB2 to be installed for RL overload protection. The generator has limited current supply. It separates the circuit from the electric grid. Unchecked short circuit, unchecked loading, it can lead to power trip. The 15 kVA can overload the 10 kVA, lead to burnout of pole transformers. Installation site at the pole transformers to be on plinth, high position, transformer room, and door locked, accessible to authorized maintenance personnel. The 13,800 volt wiring, even the neutral, return wire in the circuit, when inadvertently shot to ground, it can lead to electric spark hazard. All wiring termination screws, nuts to be tightened for good conduction of current to avoid arcing. The pole transformers are to be isolated from the ground with high voltage 20,000 volt insulation mat. This AC circuit analysis is based on theoretical simulated loads. I have not done tests to verify to validate the result. Caution: high voltage 14,400 volt is known to produce electric sparks touching metal surfaces and earthing to earth ground. Caution must be taken Do not touch any of the wiring in the circuit. Check all wiring terminations. Screws tightened. Wires securely fastened. Cables properly insulated prior to power on. To prevent electrical arcing, prevent current leakage. The pole transformers must have labeled high voltage 14,400 volt AC to alert end users. Insulation site to be on plinth, high position, 20,000 volt insulation mat, lock-in room with high voltage 14,400 volt sign. Testing, servicing, repair, maintenance to be done by experienced, qualified personnel. Keep out of children, keep out of aerosol, flammable items away from the test site, test benches. Take same precautions as we would for any electrical appliances. Thank you for watching. This completes my presentation. I wish this presentation to be useful to the knowledge seekers, electrical engineers, students, researchers, for continued research, for practical use of the circuit. Thank you, Gerard Morin, for the knowledge on pole transformers over unity circuit. Thank you, Marc Belanger. Thank you, YouTube. Thank you, knowledge seekers. Thank you, my wife, Doris. Have a good day. Peace to the world.